Hello everyone. Thank you for coming to my presentation. My name is Jelena, and today I'm going to talk to you about security of machine learning. So let's get going. First, I would like to explain a bit about my background and why am I even discussing this topic. Basically, I first finished my bachelor and master studies at electrical and computer engineering at Faculty of Technical Science in Novi Sad. And then I went to Faculty of Informatics in Switzerland, where I did my PhD, mainly in the topic of malware detection. In addition to this, I also worked with face recognition systems during my internship in IBM. And also, I did a bit of work in anomaly detection and failure prediction as a part of our collaboration back in Switzerland with EPFL. The other aspect that I'm working on now as a postdoc at Vienna University of Technology is security of machine learning. Within this aspect, I'm looking into attacks that can be performed on machine learning systems, and at the same time into defenses and how can we protect from such attacks. Finally, with respect to this, I'm trying to understand what are the efficient ways to increase trust in machine learning, and this is mainly through explainable machine learning. What I find particularly interesting is that when we take into account specific application domains, new challenges arise. And with respect to this, I'm particularly interested into mobile and embedded systems, which are constrained devices, and the applying machine learning in them is a challenging task due to various constraints, mostly in battery, but also in terms of memory and CPU. But today I'm going to discuss security of a machine learning aspect of this, and I would like to start first by saying why do we need secure machine learning? We definitely need machine learning, right? Machine learning is something that is being more and more deployed in practice. At the same time, it is frequently used in automated manner, and in recent years, it is even being used to protect safety critical systems. But at the same time, machine learning is same as any other software, which means that it has vulnerabilities that can be exploited. And recent research in adversarial machine learning showed us that machine learning actually has some inherent weaknesses and blind spots that can be abused. And at the end, this is a black box approach, so it is difficult to understand how does it make decisions that it makes. So the main goal of this talk is to convey that before relying on machine learning and before deploying it in practice, we have to understand what are the weaknesses of it and where do these systems fail. So when it comes to the deployment of machine learning in practice, we can say that there are a couple of steps to that. And the first step is actually training. In this step, what happens is that we first have a data set that is representative for the domain of interest. And then based on this data set, we try to understand which features make sense to use here. This is something that is called feature selection process. After this process, we come to something that is called selection of the best performing algorithms. And here we test a couple of systems, and based on their performance with respect to some metric that we use and like, we find one and we say, okay, this is a system I like. I'm going into the deployment stage with it, and here I basically hope for the best. I hope that the system performs well in the deployment. But what can happen is that it is not so easy. And from the security point of view, there are three things that matter. And these things are called confidentiality, integrity, and availability. And the machine learning can be affected in many different ways. First one is related to confidentiality. And with within this context is also about privacy of data. And what can happen here is that at the deployment stage, a system that is running can be somehow stolen, which basically means that its functionality is duplicated. The system can be used to extract sensitive information about data that is used for training. This is something that is called model inversion, and at the end here, it can happen that there is a way to say if some instance was used in a training data set or not. With respect to the integrity, what can happen is that the system can be poisoned in the training phase in such a way that backdoors or neural network trojans are injected in the system so that later they can be activated. The other thing that can happen here is also evasion, and this happens in the deployment stage, and it basically means that there are some instances that are able to completely evade machine learning system. Finally, there is availability, and here, again, it can happen that the system is poisoned in the training phase in a way that the misclassification error is increased at the later stages. And also in the deployment stage, it can happen that the system is abused in such a way that false positives are so increased that basically a system is under denial of service, or that it's the trust that one can place in the system is completely lost, so it's basically a useless system. During this talk, I will just briefly talk about poisoning and mostly about evasion, because these attacks I find the most interesting and the most relevant at this particular point. So, poisoning attack. What can happen is that here there is a malicious attacker that is playing with training data. This guy is somehow able to either inject new instances into the data set, is able to somehow modify them, or is able to completely remove them. As a result of such manipulations, what happens is that the decision boundary of the system changes, right? So there is something like this, and this means that the system later on in the deployment is performing worse than what we expected. So it is increasing misclassifications. Another example of poisoning attack we have here, it is basically Google Translate, in which someone who got a translation in French for "I love cheese" is now saying that translation of "you are a horse" is a better fitting instance for this scenario. So he's a guy who is able to somehow poison the training set. As I previously mentioned, the other attack that is very interesting is Evasion Attack. What makes this attack interesting is that it happens at the deployment stage. So the attacker does not need access to training data. And here the attacker somehow manages to completely abuse machine learning system in a way that is saying that some instance is legitimate, although the instance actually performs an attack or does some malicious behavior. Such instance in the adversarial machine learning domain is called adversarial sample, and it is referring to the fact that it is a maliciously created instance with a goal to cause misclassification on a machine learning based system. So here we have one example of glasses. These glasses are basically example of adversarial attack. So these are instances that are created maliciously with the goal that someone who wears them is misclassified. And here we have a guy who is 41 years old, a white man, that wearing these glasses manages to trick a face recognition system based on deep neural network to believe that this is actually Mila Jovovich, which for humans probably wouldn't happen so easily, but here machine learning is actually even confident that this is Mila Jovovich. So in addition to existence of such attacks, it is also shown that these attacks can be implemented in the physical world. And what I have here in this figure is a set of images of a turtle that it is basically 3D printed turtle that is to which the malicious perturbations are applied with a goal to cause misclassifications. And what we can see here is that misclassifications have happened in all the cases. And this turtle was classified as a rifle almost all the time, and not even a single time as a turtle. And what is interesting here is that the very same system, without these adversarial perturbations, was able to say with 100% that this is a turtle, right? Something that human sees immediately. So if the turtle does not worry you, or if you think it's perfectly fine if it's misclassified, there is another example that can also happen in practice that I find a bit more worrying. What we have here is a stop sign that by human is classified correctly as a stop sign. Also, machine learning system is able to tell us, yes, of course, it's a stop sign. We should stop our autonomous car here. But when these malicious perturbations are added to a stop sign, something interesting happens. And what happens here is that human, of course, still sees it's a stop sign, but our machine learning-based system is strict. And this machine learning system says, yeah, go. This is an instance of a sign that allows us to go. So to me, this is worrying. And what is even more worrying is that such perturbations can be generated in an automated manner. So it is not complicated to generate such manipulations to be added to images. And in addition to this, such manipulations also transfer. So if one is able to create a set of manipulations that work on a stop sign, this set of manipulations can be applied also to other images and trick also other machine learning-based systems into causing misclassifications. So how can we automate these attacks? Well, basically, there are currently 3 main methods that this can be done. These 3 methods are different. They have different characteristics. For example, FGSM is the first attack that appeared a couple of years ago. And this system is very fast. It can create adversarial samples quickly. But what happens with it is that sometimes the perturbations that it makes on images are visible to human eye. So it is not perfect in that sense. But recently, a very, very powerful attack appeared that is called Carlini-Wagner. And this attack now creates permutations that are almost invisible to human eye and still cause misclassifications. Just the problem with this one is that it is slower than FGSM and JSMA other attacks. So one thing that is the same with all of these attacks are that they are research efforts that are publicly available, and people can play with them and use these tools. And here I'm listing just few libraries that are having these attacks implemented, so everyone can use them to generate attacks, but everyone can also use them to check various defenses. And with respect to this, we have the SecML and Fullbox. These are research efforts, but for example, CleverHands is a library from Google, and also IBM has its own library that allows us to check all of this. So, as I previously mentioned, these attacks exist. These attacks can be automated, but these attacks also transfer. And the way why they transfer is because of the existence of a phenomena called transferability. And this phenomena was discovered around 5 years ago, and it showed that the instances misclassified on one machine learning system frequently misclassify also on other machine learning systems. And here what is important to say is that this applies between same machine learning techniques. So if I'm attacking your neural network-based system and I I craft adversarial instances on neural network, it works. But it also works among other machine learning systems. So if I'm attacking your neural network-based system with my logistic regression-based system, the attacks still transfer. It is possible that they transfer. And here I'm showing some of the effects of this transferability phenomena. So here, now I don't have a pointer, but in the x-axis you can see a target machine learning technique, which means that is something that is deployed. And on the y-axis there is source machine learning technique. This is a technique that I use privately to craft instances that misclassify. And for example, if there is an SVM on the target as a target machine learning technique, and I use SVM to craft attacks, these attacks transfer with 100% probability. If I, for example, have logistic regression, we have a number like 91, but the important thing here is that we can see that these attacks frequently transfer. They don't always transfer among each algorithm, but this phenomenon exists and it causes instances to misclassify. So why such attacks happen? This is a question that is still being answered in the research community. It is an active area of research, and just some of the recent conclusions are that since the learning algorithms always choose a set of features that are representative for the task that they solve, the very same system becomes very sensitive to changes in those features. So sometimes even small modifications on such features can cause big changes in terms of classification outcome. The other reasoning is also that although machine learning systems can be different, most of them somehow picks up similar set of features. And this is basically the cause of the transferability among these attacks. So the question arises if we can actually defend against this, and if yes, how? How can we do it? With respect to the poisoning attacks, there are different ways that are currently proposed. First defense is something that is called the RONI. It is a reject on negative impact. And the main reasoning behind this defense is that if we see that there is an instance that is significantly different than others, we don't accept it. And the other way is also that if we haven't seen instance in training phase, we avoid to assign that instance as legitimate. The other way that we can also defend is that we perform something that is called data sanitization, and it is basically just applying outlier detection methods and data filtering and trying to understand if something is different that we are facing here. The space of defenses against evasion attacks is much bigger. There are much more defenses because these attacks are happening at the deployment stage, so they are more serious and they can cause more damage. And what people did here is that they first said, well, if I use an ensemble of classifiers, then I'm protected, right? But this doesn't actually work. The main reason that this doesn't work is because of transferability, and these attacks actually transfer. The other thing that people said is that, well, I have now adversarial samples, now I know how they look, I can generate them using some of the techniques, mark them as such, and retrain the system. And this somewhat works, but is not efficient because the space of these adversarial samples is unlimited space. So it is not perfect. There is something that is called defensive distillation. It is a technique that proposed to somehow smooth the decision boundaries of classifiers, and in this way make them less sensitive to changes that can cause misclassifications. But this is also proven that it is not perfect. Some other people said, let's reduce dimensionality of input space so that the attacker has a smaller attack surface, less features to modify, and thus possibly cause misclassifications. The next thing that is proposed is regularization, and this means that we basically penalize those features that are marked as somehow very important, and we avoid assigning a very important value to them. Of course, the problem with this is that we are creating a trade-off between accuracy and robustness in this way. Finally, there is also the way to basically use the membership score, so basically distance to the decision boundary, as a feature in order to identify adversarial samples, and this is basically our work from TU Wien, but also this has some problems, let's say. And in some recent work from 2 years ago has shown that all these defenses can be evaded in one way or another. So basically, there is a problem with each of them. The other important aspect that arises from the same paper is that existing defenses lack thorough security evaluation. So some people said, okay, my defense work amazing, but they test just one data set, or they test just one attack, not all of them, and not the strongest one. And finally, the conclusion with respect to this is that the adversarial samples are much more difficult to detect and to protect from than what was initially thought. So all this area remains still an open research problem. Apart from the security of machine learning and privacy aspects that at the beginning I briefly mentioned, there are also other vulnerabilities that we should think about and try to resolve. And first of them is who is responsible for what machine learning does. So who is responsible for decisions of machine learning. Then the question of how did machine learning perform something, what was the logic behind, still remains. And finally, there are also problems with bias and fairness with machine learning systems deployed in practice. So this brings me to the takeaways of my presentation. And the first thing that I would like to stress again is that security of machine learning is of growing concern. And there are different attacks proposed that can evade machine learning-based systems. And these attacks, not just that they exist, they transfer, and their generation can be done in an automated manner. The next thing is that active countermeasures in order to secure machine learning systems should definitely be adopted, but we still don't know which ones, and we still lack the effective defenses with respect to this. And with respect to improvement of such defenses, we should definitely look into the security domain and adopt more security practices from there. Finally, there are still many open problems, and just some examples are that we need better defenses, there is a problem with privacy, lack of transparency, and so on. And future work in this domain is absolutely needed. So if some of you is passionate about it, you are very, very welcome to join on board and work on adversarial machine learning. So with this, I conclude my presentation. I'm looking forward to hear your questions, and if there is some question you would like to discuss, we can do it maybe offline, or you can contact me on some of the social networks. Thank you. Hvala svima.
Yeah. Just a second till I open the questions.
Sorry.
Just a second till I open the questions.
Okay, sure.
There are a couple of them, I think. Okay, it's working slowly.
Very long questions.
No. Okay. What is the percentage of attacks for each of the categories from the list given in the beginning of the page training and deployment table?
What is the percent? Sorry?
What is the percentage of attacks for each of the categories from the list given in the beginning of the page training and deployment table?
Well, I don't think that such information exists. What can be said is that poisoning attacks are more difficult to implement. So I would say that they are less frequent because one has to somehow have access to training data and poison it. On the other side, evasion attacks happen at the deployment time, so everyone in a way has a chance to send something and hope that it's misclassified. Definitely more in the evasion part. Yeah, so when it comes to backdoors, it is not really publicly available. Who did it? How did he perform this action? And so it is very, very difficult to answer, and I'm not sure that the answer actually exists. It's more related to each attack particularly.
How often are these attacks happening? Are there any reports on the amounts of the attacks, and how would you detect them?
So how
often
yes?
are these attacks happening?
Okay.
Are there any reports on the amounts of the attacks, and how would we detect them?
Okay, so in particular with evasion attacks, they happen, and the way how these methods were actually proposed and validated is using publicly available face recognition systems. So how often someone will try to do this, I don't think it's a public information. It is not really known, but it can be done. So they can happen. At this point, I would say maybe not even so often, because not so many people know about them, is interested in them, but how difficult or how easy it is to perform these attacks is another question, and I think that it is relatively easy, and even technically skilled person can now do it using all the open source libraries and so.
Do these attacks exist for non-image processing machine learning, like recommendation systems?
Like recommendation systems, I'm not sure. I'm not following recommendation systems, but these attacks are shown to exist for malware detectors, intrusion detectors, and more non-image classification domains are being published now that they suffer from these attacks. Also, for example, for audio examples and systems based on voice.
Do you have any popular example where machine learning was attacked?
I think that there was the, well, I don't want to say now, but I think that some of the one of the big publicly available cloud services that offers machine learning was successfully attacked using these techniques.
So are there very often? I mean, what do you say?
This is something that they wouldn't tell us, right? They are not interested that we know. So we don't have such a number.
Okay, thank you.
Thank you.
Is your certificate?
Great, thanks a lot. Thank you.
Thank you, Jelena.